Hi, I'm Lauri Koskinen, Professor of Systems of Chip at University of Oulu. Today I'm going to talk about approximate processors and are they even possible. First, I'll start with the general minimum energy point and in more general low energy and low power for digital logics, which of course all processors are comprised of. Let's think about low power in general. So, as everybody probably knows, the basic energy and power equations shown on the top. Dynamic energy is squared, and then leakage energy and therefore static energy is about linear. And when you go into lower voltages, you see the effect of this quadratic voltage here. And you do find a minimum energy point, which has been proven in many ways, both chips and simulations in the past. This is a very interesting way to lower power, where nominal voltages, depending on your process, would be somewhere around the 1 volt range. You can go into low voltage, which is in most process design kits available nowadays. But then near threshold, going down into 0.4, 0.5 volts is usually not still possible. We'll see in a second what the reason for that is. But if you can go there, there's theoretically a very nice energy reduction available, going down theoretically about 10x. So why doesn't everybody use near threshold? Well, one reason is, of course, that, as you saw in the previous slide, that the chips slow down. But the main problem is variance. And as you see from this slide, when you go down to lower voltages, if you look at the different corners and especially the within die variation within the corners, your variance really blows up. Note the logarithmic scale here. You really do see 100x difference in a single transistor. The variance problem is well known already for 20-ish years. You have a multitude of problems when doing the chips with lithography. You have the thickness of layers, then how the metals become, are they ideal or something different? This, of course, affects parasitics. And then implantation and the number of atoms. When the atoms start to become very small, then even the difference of a few atoms can be a big change. And the main thing that you see the result of variance, even in nominal voltages, is power and speed. So this from AMD processors, you do see even in an older process a 4x difference in leakage and therefore static power and a less than 50% difference in speed over a big number of transistors. And one reason for this is the variance in the size of the length of the transistor gate and how that affects then the leakage current. And you end up with, when you have a slow transistor, that will limit your speed, and the fastest transistors will then at the same time leak the most. That's when you end up with this kind of a curve. It also depends on different circuit types, and the SRAM cells are the most susceptible to variance. And that, of course, is dependent on the short paths that you see in SRAM. So you do only have a few transistors in the path here, and then some of them can become dominant. And then if you see a big variance in one of those transistors, then that will show up then in the cell. And of course, in SRAM, you do have millions of instances of exactly the same cells in exactly the same places. That means that you will get high and high outliers, most likely 6 sigma outliers. And you end up with, if you want to go to minimum voltage, it will be higher for SRAM than it is logic. Logic, on the other hand, is easier. The main reason for that is the central limit theorem. So when you have lots of independent variables, the transistors here. When there's independent variance in them, they tend to, on the average, to cancel each other out. So a path like this will have a more narrow distribution than the single element. Of course, flip-flops define your setup and hold times, and they will therefore be more susceptible to variance. One solution to variance tolerance is what would be called better than worst case design. That means that if this is your distribution of your chips, then you actually run them at a voltage where some of those chips fail. And this has been well known in an SRAM design for tens of years, where there are a number of ECC, that is error correction solutions, which can then make, on average, the memory work better, either faster or on a lower voltage. Redundancy is also another well-known solution. But how do you do this? Well, you basically set the voltage at a point for the whole chip or the whole processor at a point where you know by design that some of them will fail. But then you have different methods, through which I'll go in just a second, of either correcting the errors or then understanding that your system can tolerate those number of errors. And if you start to tolerate the errors, then one thing that it leads to is approximate computing, which has been known for a while, but there is not a really general use case for approximate computing. And let's see whether we can find one. But first, some background on error toleration. So error toleration has been known for a while. There are a number of different cases like binning. For example, Intel in their multi-core processors, if some of those processors don't work or are too slow, they actually just basically cut them off and sell that piece in a lower core part. But there are other things like redundancy, duplicate and compare, software solutions such as checkpoints, information redundancy, algorithmic techniques. But all of them require monitors. So you really do have to understand where the error happens and when you have to correct it. And there are a number of different cases, both in situ monitoring based on temperature, maybe voltage, critical path latency, or operational monitoring such as BIST techniques or timing error detection. I'll look at the latter one next. But first, like I said, this is actually an old solution. So this has been known for tens of years. If we go back to the SPARC 64 processor, 30 years old or more now, it had a number of parity and error correction solutions already on chip back then, mainly because the chip was so big, so they probably saw yield issues with a big chip. I mentioned timing error detection. This is an interesting academic solution which has originally been introduced in the University of Michigan, but many groups like myself have been doing solutions on it. And the idea is to run below the point of first failure, so basically running so that you do get some errors, and then you correct these errors. The IPC of the pipeline of the processor starts to drop at some point when you get more and more errors, and then the error correction starts to take way too much energy. Somewhere on this point, you have an optimal voltage where you are running with a small number of errors, and if you can run at that point, then that is a good solution. The original case was instruction replay. I'll go through that in just a second. So basically you run the instruction again, but you can do this with DVF solutions, clock adjustment, VDD adjustment, and then if you go into approximate techniques, you can interpolate the signal or replace the signal. And let's look at these a bit. The monitoring, as I mentioned, was very important in this case. In the original Razor, you had what is basically a shadow monitor where you had a delayed signal, and if the signal changes late, then you have a delayed signal of that, and then you compare these two, and then that flags an error if they are different. And if everything happens nicely before the clock edge, then of course you do not flag an error. And they got nice results. This is already somewhat old results where in 0.2% reduction in IPC, which corresponded to a 0.04 error rate, they got about a 30% energy reduction, and that was even 5% past the point of first failure. So ultimately, you'd like to move somewhere here and keep your chip at that point. This table unfortunately shows the inherent problem with all of the Razor type solutions. They do need a number of cycles to affect the instruction replay. And you can see in the table that it goes from 7 to 9 cycles depending on the result, both academic and Intel and ARM solutions. And therefore, these type of solutions haven't been seen in commercial applications. This has been solved even in commercial solutions, but as we are talking about Approximate, let's go more into that. The idea between Approximate, as it has been presented previously, is that many algorithms are robust to noise. The best case example probably would be video, where a human can easily understand if there is noise in the video or if the picture quality is bad, you can still understand what is happening there. And this is easily seen in signal to noise ratio, which quite smoothly degrades if you reduce or add noise into the process. But it also applies for machine learning. K-means, if you look at the bottom graph here, you can have errors in the computation before getting incorrect results. And of course, telecom algorithms, which are by design robust to noise, so you do see the same behavior there. And this has been shown in many solutions. This solution from my group back in the day, where we had a VLI-W processor with a replacement engine, where if we saw that there was an error in one of these computational engines, then we just replaced that with a data value that had been decided previously. For example, if you are looking at the probability of some signal in telecom, then you put the probability at 0.5. And this worked with a number of different algorithms, just Bayes regression and K-means, where you could have the timing errors and the chip didn't still fail. And you can see that you have perhaps somewhat smaller values here than you had in Razor, but still the same general idea. Another solution that has been presented is approximate error correction, which requires continuous signals. So basically, if you have an error, then you just interpolate or do something else between the values. And for example, Paul Wotmog from ARM has showed nice values where he exactly interpolated between values and got a gigahertz processor with some over 30% energy reduction values. So similar values than the original Razor paper. But this has a lower cycle penalty than Razor and is therefore quite interesting. One interesting solution, again already somewhat old, is statistical error compensation, where you have a big main block of computation and then you have an estimator which estimates the correct result. And again, if you keep the error correction energy low enough and you can at the same time lower the main value block, then you get energy benefits exactly like in Razor. And this was shown in University of Illinois with a telecom algorithm where basically the sub-implementations, the main block was a bandpass filter and then an estimator, which was a median filter, basically getting the average result. They had a nice 3.9 or maybe 4x energy reduction in the results. But again, this is only applicable to some results that are on basically the telecommunication lines of fields and can be then changed with the estimator that you require in this block. Of course, Approximate needs also software, and a nice solution has been shown in University of Washington, where they design both approximate and precise data type qualifiers in Java. You can also do this with C or C++. And then they basically inherit that class throughout the code. And if you combine in some way precise and approximate values, then the end result becomes approximate. And there's a small code here. This is a nice way of thinking, but if it of course needs its own compiler and in likelihood a big rewrite of existing code. So ideally you'd want to have the processor such that it doesn't require a rewrite of code and a rewrite of compiler, so you basically keep the approximate values below the hood. So let's see if that can be done. If we look at a general case of a processor with your data path and your memories and your control, this can be your basic RISC processor, it can be your DSP and even your GPU, which would of course be much more parallel. If you get errors in the data path, in the LSP, that is well understood. It is basically noise, and even in the MSP, you can think of it as high magnitude noise. Error in the addressing, of course, will not be the same. So if your data memory addressing is incorrect, then it probably will look like a very high magnitude noise in the end result. And the biggest problem is the program flow. If there is an error in the instruction memory or the control, then that means that the whole program flow will be disturbed and in likelihood will not work. So how general are these solutions? One problem is that you have many critical paths into the memory. As we saw previously, the memory is somewhat slower, also works at a higher voltage usually. Then that means that you will have a number of critical paths into the memory. And that is not a good result, and you need to really think about how you can do that in the memory. So can we even think about a PDF for the timing noise? And this result, again, from my group, is that you do see a very fast reduction in the signal quality. So if one gate fails, usually many gates fail. And this is a measurement results from a RISC CPU with different frequencies. And you really do see the number of errors going up fast, and you really have to be able to catch this. And if you are simulating this as noise, it is an interesting question how to give a PDF to such a waterfall type of distribution. The reason for this is, of course, the flip-flops hold and or setup time violation, where the flip-flop becomes more or less metastable and can take an infinite or less amount of time to decide on its output. So you do get the errors. Unfortunately, I do not have the exact answer for you because this is still under process in our group, but we will roll out processor types with multiple different solutions. As you saw in the previous one, you only had one type of solution, usually on the data path. We'll have both algorithmic and timing solutions in the data path, algorithmic solutions in the memory, and then redundancy in the control and instruction memory, and thereby getting a full processor architecture which is approximate and can handle a number of errors at low voltage. And with that, thank you for listening. Next time we'll have a full solution for you guys. See you then.